All right, guys, here are some pressure and fluids problems. The first problem we're going to look at is a problem dealing with Archimedes' principle. The idea that when you put a fluid in water, the weight of the water pushed out of the way or displaced by the fluid is equal to what's called the buoyant force, the force that pushes upward on the object that's submerged in the fluid. Problem 1 says the apparent weight of a fishing sinker is 4.9 newtons. If its real weight in air is 12 newtons, what buoyant force acts on the sinker? Here's the thing you got to know. The 12 newtons is the real weight. The 4.9 newtons is how much that it seems to weigh when it's in the water. So the difference between those two, the difference between 12 and 4.9, let's just subtract those, should give us 7.1. That 7.1 newtons is the upward buoyant force acting on the sinker. Now to do problem number 2, it's going to be a little bit more detailed. Remember that the weight of the water displaced is the buoyant force. What we're trying to find in problem 2 is the volume of the water that's displaced. So we know the water weighs 7.1 newtons. We need to figure out what is the volume of that 7.1 newtons. So we're going to go to a slide where we have a little space. Some things that we need to remember. We need to remember the equation for what's called the weight density of water, or the weight density of anything for that matter. The weight density is equal to the weight of the fluid displaced divided by the volume of the fluid displaced. For water, the numerical value of the weight density is 9,800 newtons per cubic meter. So in this problem, we know that there are 7.1 newtons of water displaced. That's the weight of water displaced. We know the weight density of the water displaced. So we can solve for V. So if we do a little algebra and rearrange this equation, you should see that the volume equals to the weight divided by the weight density. So in this case, we're going to have 9,800 newtons per meter cubed. That's the weight density of water. We're dividing that into the weight of the water displaced. So let me move that a little bit out of the way there. So let's divide the weight of the water displaced, 7.1 newtons, by the weight density of water, 9,800 newtons per cubic meter. Paying attention to the fact that the newtons are going to cancel out. We're going to be left with a unit of cubic meters. So let's go 7.1 divided by 9,800. And we end up with the proper significant digits, which for this problem was 2, with an answer of 7.2 times 10 to the minus 4 cubic meters. That's the volume of our water displaced, which would also be the volume of the object, the sinker in this problem, if the sinker is all the way under the water. All right, so let's look at problem 3 this time. Actually, it's listed as problem 4 up here. Each of the paws of a dog, the dog's mass is 20 kilograms, has a surface area of 0.00250 square meters. What force does the dog apply to the ground when the dog is standing? And what pressure in pascals does the dog apply to the ground with each paw? So let's go to another slide so we have a little room. Here's what we know in this problem. We know the mass of the dog. The dog's mass is 20 kilograms. From that mass, we can find the weight. We know that weight equals mass times gravity. So let's go 20 times 9.8, and we get 196 newtons as the weight. That weight is the force the dog applies to the ground. That's the answer to part A of our problem. The weight is the force the dog applies to the ground. We're assuming here that this is a four-legged dog. So that weight is going to get divided evenly amongst its four legs. So if we go 196 divided by 4, that's 49 newtons of force on each leg, or each paw. You should know that pressure equals force divided by area. We're trying to find the pressure at each paw. So if we go pressure equals the force acting on each paw, which is 49 newtons, divided by the area of each paw, which our problem tells us is 0.00250, and that's in square meters. If we go ahead and divide that out, we end up with a pressure of 19,600. We need 3 significant digits in this problem, so this is going to be correct. We have newtons per square meter. The name for that unit is the Pascal. So that will be our answer for part B. All right, this time we're going to look at the raft problem, which is labeled as number 5 here. Notice it says we have a raft whose bottom has an area of 100 square meters. It floats in water with 20 centimeters of the raft underwater. We want to find the weight of the raft, the volume of the underwater portion of the raft, and the buoyant force. So again, let's go to a slide with some space, figure out what we can. First of all, try to draw a picture. Picture is always helpful when you're working this kind of problem. So we're going to try to go 3D here. My board is a little off, so my cube here doesn't look so good. But here's what we know. We know the area here at the bottom of the raft has the bottom of the raft has an area of 100 square meters. We also know that this thing sinks under the water 20 centimeters. Now I'm going to write that as 0.20 meters. That's the area of the raft that goes underneath the water, the height of the raft that goes underneath the water. But it floats after it does that. So what we want to know again is the weight of the raft, the volume of the underwater portion of the raft, and the buoyant force. Well, the volume's pretty easy. You guys should know that volume is length times width times height. Or another way of thinking about it, since this bottom is a rectangle, they found the area by going length times width. So another way to write volume would be area times height. Area of the base times the height. So in this particular problem, we're going to go volume equals 100 meters squared times 0.2 meters. So when we multiply that out, we end up with 20 cubic meters. That is not only the volume of the raft that's under the water, it's also the volume of the water displaced. That's our answer to part B. But here's the key thing. That's the volume of the water displaced. We know that the buoyant force is equal to the weight of the water displaced. So we need to know how much does 20 cubic meters of water weigh. If you watched me work problem 1 and 2, you saw me talk about the weight density equation. And that the weight density of a fluid is equal to the weight of the fluid divided by the volume of the fluid. And we know the magic number for water in weight density is 9,800 newtons per cubic meter. That's dW. We're trying to find in this problem the weight of the water displaced, because we know that's equal to the buoyant force. So we're going to solve for W. So the weight of the fluid displaced is going to be equal to the weight density of the fluid times the volume. So in our problem, we need to say 9,800, the weight density of water, times the volume of water displaced, which is the same as the volume of the raft that's under the water, 20. Cancel out cubic meters. And if we do a little math on this, 9,800 times 20, we end up with 196,000 newtons. That's the weight of the water displaced. That's also the buoyant force. So that is our answer to part C. But the key thing in this problem is that this raft is floating. If it's floating, the buoyant force must also be equal to the weight of the thing that is floating, which in this problem is the raft. So this is not only our answer to part C, it's also answer to part A. If something floats, the weight of the water displaced is equal to the buoyant force and the weight of the object. If something sinks, the weight of the water displaced is still equal to the buoyant force, but the weight of the object is greater than that buoyant force. That's why it continues to move down or sink. All right, let's go ahead and look at the problem up here labeled 6, the one about the sphere. This tells us that a sphere has a volume of 140 cubic centimeters. It's completely under the water and then released. What's the acceleration of the ball if the mass of the ball is 215 grams? Give the acceleration in meters per second squared. Also describe the motion of the ball, in which direction is the ball accelerating and why. So again, let's go to a clear slide and talk about what we know. We know the volume of the sphere, 140 centimeters cubed. We know the mass of the sphere, 215 grams. I'm going to go ahead and change that into kilograms. And I'm going to go ahead and multiply that by 9.8 to get the weight. So the weight of this thing is 2.11 newtons. Now here's the thing. We know that this ball is completely underwater. It's got a volume of 140 cubic centimeters. So this volume is not only the volume of the ball, it's also the volume of the water displaced by the ball. What we need to know, first of all, we need to find a buoyant force. And we know the buoyant force is equal to the weight of the water displaced. So we need to know how much does 140 cubic centimeters of water weigh. To figure that out, we're going to go to density. And there's several values of density we could use. We could use weight density, but in this case, since this is already in cubic centimeters, it would make sense to use the value for the density of water that's in cubic centimeters. And hopefully you know that the density of water is 1 gram per centimeter cubed. Which means if we displace 140 cubic centimeters of water, we displace 140 grams of water, which is 0.140 kilograms. But we don't need to know the mass of the water displaced. We need to know the weight of the water displaced. So let's take this 0.140, multiply it by 9.8, and get a weight of the water displaced, or a buoyant force, of 1.372. Again, the weight of the water displaced by an object is the buoyant force, and that buoyant force is acting up on this object, which in our problem is a sphere. So we've got this force acting up, but we also have a force acting down. The weight's acting down. Notice that those two are not equal. The weight's bigger than the buoyant force. So this should tell you that this thing is going to sink. It's going to accelerate downward. And you guys all know that to find the acceleration, we first need to find the net force. So to find that, we're going to take our weight and subtract from it our buoyant force. We're going to take our downward forces, which are the biggest, and subtract from those our upward forces, which are smaller. So 2.11 minus 1.372, we end up with a net force of 0.738 newtons. Now, you guys all know that acceleration, according to Newton's second law, is equal to F net over m. So in this problem, we're going to take our net force, 0.738 newtons, and we're going to divide that by our mass, the mass of our marble, which was 0.215 kilograms. That does need to be in kilograms so that our newtons, remember a newton is a kilogram times a meter per second square, so that when we do the division of units here, we'll get meters per second square for our units. So we're going to go 0.738 divided by 0.215, and we're going to end up with an acceleration of 3.43. Actually, on this problem, we need 4 significant digits, so 3.433. Our units are going to be meters per second square. And something we need to make sure we add, we know that the downward force is bigger than the upward force, which is telling us that this object is going to accelerate down, it's going to sink. So we can either put a negative in front of this answer, or just a downward arrow, or we can just say down. But the last part of the question says describe the motion of the ball. The ball is going to sink, and it's going to accelerate at this rate as it sinks. All right, the last problem we're going to look at, actually the last two, number 7 and number 8. Actually, I'm not going to work 7.